Here's an example in which we use strong induction to prove this statement. Let R be a real number, and if this expression R plus 1 over R is an integer, then for any n value that is a positive integer, R to the power n plus 1 over R to the power n is also an integer. Okay. Now, we are going to use strong induction, and obviously the base case is for n equals 1, and that is essentially true because it is given to us. R to the power 1 plus 1 over R to the power 1 is already an integer. But if you like, you can choose the base case to be 2 and actually write the case for n equals 2 as, well, R squared plus 1 over R squared as R plus 1 over R squared minus 2, because if you take the square of this, you will have R squared plus 2 times R times 1 over R plus 1 over R squared, and this here with this one is already this term. The only difference is, well, R times 1 over R is 1. The only difference here is 2. So if I subtract 2, I get this expression here. Okay. But I know that R plus 1 over R is an integer because it's given to me in the question. And if I take its square, it's also an integer. The square of an integer is an integer. And if I subtract 2, it's still an integer. Okay? So for n equals 2, this holds. R squared plus 1 over R squared is an integer. Now, in the inductive step, I'm going to use strong induction. So I'm not going to just assume this is true for n equals k. I'm going to assume this is true for n equals 1, 2, 3, 4, etc. up to k. Okay? So R plus 1 over R is an integer. R squared plus 1 over R squared is an integer. R cubed plus 1 over R cubed is an integer, etc. up to R to the power k plus 1 over R to the power k is an integer. That's my assumption. And from this assumption, I'm going to show that the value R to the power k plus 1 plus 1 over R to the power k plus 1 is also an integer. Now, I'm going to write this expression as R plus 1 over R times R to the k plus 1 over R to the k minus this. Now, how did I obtain this? If you just expand this expression, you get R to the power k plus 1, and then with this you get 1 over R to the power k minus 1. With these two, you get R to the power k minus 1, and with these two, you get 1 over R to the power k plus 1. Now, this here, together with this one, is already existing in the left-hand side. And what is different is these two here, 1 over R to the power k minus 1 plus R to k minus 1. So if I subtract this from this product, I obtain the left-hand side, right? Now, look at this expression. This I know to be an integer. This I know to be an integer based on my assumption. And this one, again, I know to be an integer, again, due to my assumption, okay? K minus 1 is here. Therefore, this expression is assumed to be an integer in the inductive step. You see, this is an integer. This is an integer. Their product must be an integer. And this here is assumed to be an integer. The difference between the two integers is clearly an integer. Therefore, this assumption here leads to, it implies that this expression here is also an integer. Therefore, I conclude that the given statement is true. This is how we use strong induction. Now, the key here is our assumption includes n values starting from 1, the base case, up to k. It includes all of them, not just k by itself. Okay? Now, as you see in the proof, we have used the value for k minus 1 here. If we would be doing ordinary mathematical induction, this wouldn't work because we wouldn't have assumed this is an integer for k minus 1. Okay, so sometimes you see strong induction leads to easier proofs. Let's look at another example in which I will actually give both proofs using ordinary induction and strong induction. And essentially, I didn't really prove it, but strong induction and mathematical induction, as we have seen the first version, are equivalent. If you can prove it using one, you can also prove it using the other. So whichever looks like easier, you can use either the ordinary induction with just assuming k, or strong induction using the assumption where the statement is true from the basis step all the way up to k. Now here, let's see the statement: prove that any amount of postage of 12 cents or more can be formed using 4-cent and 5-cent stamps. Okay, so you have two kinds of stamps worth 4 cents and 5 cents, and combining these, you are going to make up a postage amount, and we know that the postage amount will not be less than 12. Okay, so for instance, 11 you cannot make up using 4s and 5s, but 12 you can use 3/4 to make up 12. So my basis step for the strong induction, actually my basis step consists here of 4 cases: 12, 13, 14, and 15. Okay, so 12 can be obtained by 3/4, 13 can be obtained by 2/4 and the 5, 14 can be obtained by 1/4 and 2 5s, and finally 15 I can make up using 3 5s. Okay, so we just trivially see that the statement is true for 12, 13, 14, and 15. Now, in my inductive step, I'm going to assume P of n, which is the statement here, okay? And n here represents this, 12 or more, okay? Pn is true for n values greater than or equal to 12 and less than or equal to k. And k here is greater than or equal to 15, because up to 15, that's my basis step, okay? And this, I'm using strong induction, so I'm assuming P of n is true for all the values up to k. And k here is at least 15. K being at least 15 means k minus 3 is at least 12. Okay, that's the reason I have included 13, 14, 15 in my base case, because this is not going to apply if I leave them out. So k minus 3 is greater than or equal to 12, which means by my assumption, okay, P of n is true for k minus 3, whatever k is, okay? That means for k minus 3, I have a combination of 4s and 5s that I know the makes up k minus 3, okay? Therefore, to that combination, whatever that combination is, I don't need to know what that is, just add 1, 4, okay? You have already a combination that makes up k minus 3. Just add a stamp with 4 cents. That will give you a collection of k plus 1, okay? So that's it. Since I assumed this is true for up to k, and this entails it's true for k plus 1. Therefore, along with the basis step, my proof is now complete using strong induction. But as I said, it's not necessary to use strong induction. Actually, I can use ordinary induction to prove the same thing. And in my basis step, I just have P12. P12 is true because, well, clearly, using 3/4, I can make up 12. In my inductive step, now I'm going to assume Pk holds. I'm not assuming P of n holds for 12 less than or equal to n less than or equal to k, I'm assuming just P of k holds. And I'm going to show this, in fact, can imply P of k plus 1. Now, to show that, I'm going to consider two cases in which you just have 5s and you have 4s and 5s. Or, you might have only 4s, but that's not significant here. Okay, so case 1, there is at least one 4 in my combination 4k. Okay, and if there is at least one 4, it's easy because you take that 4 out. Instead of that, you just put a 5. So the total is incremented by 1, and you automatically obtain k plus 1. Okay, very good. What if there are no 4s, so that I can replace a 4 with a 5? In that case, if there are no 4s, this means you have all 5s, which means your total k is a multiple of 5, in which case it has to be at least 15. So it's not 12, it's not 13, it's not 14. Clearly, it's at least 15, or it could be 20, 25, etc. Okay? In which case, you have at least 3 5s. Okay? It cannot be less than 3 5s because it's at least 15. Okay? Therefore, take those 3 5s out. So you're subtracting 15. But in their place, put in 4 4s. So you took out 15, but you put in 16. So the result is k plus 1. Therefore, in this case also, P of k entails P of k plus 1. Along with the basis step, the proof is complete. So you see a statement we first proved with strong induction, and then we also proved it using ordinary mathematical induction.